All right, so we'll talk about sampling. The idea behind sampling is that you have to think about the world in a different way. And sampling and statisticians think about the world in a different way. We can see the world as it is right now, but that's not the world as it existed previously. And it might be a representation of what could exist in the future. But the reason we do sampling is to say, instead of looking at the world as a fixed set of absolutes, we think about the world in terms of a series of samples where we get different pieces of information, and we use those pieces of information to piece together how likely it is that something's happening. So when we talk about populations have a really strict definition. A population is the total set of items we want to analyze. And that total set of items that we want to analyze, like let's say it's a certain type of frog or a certain type of city structure or policy. Well, and you might not ever be able to get a complete view of all the population because it existed in the past and exists into the future. So we have to draw boundaries around that. And once we draw boundaries around that population, it limits the population. So we really don't do that very well. A population, think of it as every one of those individuals. And the way that we summarize populations is by using parameters. So a population parameter, like this one down here, like mu, that's the average something in a population. This little circle with a dealie right on the top of it, that is the standard deviation of a population. Or capital N, that's the total number of individuals in a population. But they're called parameters. So populations have parameters, and samples have statistics. So samples have statistics, and a sample is a subset of the population. So if we draw a boundary around the population, and we say we want to limit to a certain time or a certain area or a certain whatever, then we draw this boundary around the population and we can draw a sample from that. That's called a sampling frame. And the sampling frame helps us understand the extent to which we can make inferences about the bigger population based on the sample we draw. In other words, we go out and we grab a sample and it tells us some information. Well, the sampling frame, the boundary or that delineation, but that has sort of bounded the population, that sample frame will tell us whether or not we can take that information and project it into the future or maybe look into the past. And the way that we summarize samples is using statistics. So the corresponding statistic for the mu, this X bar, is the sample mean, and S is the sample standard deviation, and a small n is the sample size in terms of the number of individuals in that sample. So what we do is we take sample statistics. Statistics are those measures that summarize a sample, and we use those statistics to make inferences about a population. So sample statistics are representative, if we do it right, of population parameters. So that's just vocab. Okay. Now, sampling error is the difference that exists between the sample and what we would have obtained if we'd studied the entire population. And sampling error is what we want to minimize. So we want to do some sampling procedure that's going to help us best reflect the population. And there's some things that we know and some things we don't know about how close our sample will be to approximating that population. So if we know that things are separating us from, or if we know that things are increasing our sampling error, we should do something in our sampling procedure to minimize that sampling error. We'll talk about some of those procedures in a few minutes. But there will always be some error between our sample and the population parameter just because there's variation in the population. So in other words, if I draw a sample, it will be on average multiple times over very reflective of the population. But if I draw one sample, I might get a huge outlier or a really, really rare event and a couple of events that are pretty normal. Or I might draw two really, really random points on opposite ends that makes that sample not very representative. But overall, if I have a relatively unbiased sampling procedure, as I take multiple samples, the average of those samples will give us a pretty good representation of what the population looks like. So there are questions about like, how confident do we want to be that our sample is reflective of the population? And the general advice is the larger sample size, the more samples you take, you're going to be more close to the population, or in other words, you're going to get a smaller sampling error. So as we take more and more samples, the average of those samples is going to even out any of that sampling error that would have occurred through randomness. So we take more of them, then our sampling error is going to shrink. So a representative sample is a sample that reflects the bigger population. And bias is any error that's introduced through a sampling method that would affect our estimate of the true population. So in other words, bias is going to affect our sampling error. And we can see systemic bias, or we can have random bias. So systemic bias is something that we're doing in our procedure that's going to affect the kind of sample that we draw. We want to minimize systemic bias. And we can think through our procedure. We can bounce ideas off of other people. There's some tried and true methods to reduce systemic bias. That's just something we're going to have to work out in the methods portion. But there is random bias. Things that just randomly occur, natural variation that's going to mess up whether or not our sample is going to be representative. We can't really do anything about random bias. So why do we take samples? We take samples because we probably can't count the true population. It might be impossible or unmanageable. For example, how do we census a homeless population? We do it, but we miss people. We miss people who are hiding. We miss people who are not in places where we know to look. We miss people who, well, all sorts of reasons why we miss homeless population. But if we took a sample, we might be able to get a good estimate based on the laws of probability about how close we are to what the population of homelessness looks like. And I think about people who do endangered species sampling. We're talking about very, very rare plants or animals or whatever it is. If we tried to count every one of those things, it would take us forever. So we take a sample so that we can get a good guess about what could be out there, potentially or hypothetically, because otherwise we'd just waste resources trying to find every individual one. And samples overall help us use fewer resources to get a reasonably close estimate of what the population looks like, or some population parameter. And the best part about sampling is we get to decide what we think is reasonable. So people always ask, well, how many do you need to take? Well, it depends, and we'll talk about through that. So there's two sort of concepts at play here. One is the central limit theorem. And what it says is the distribution of the sample mean is approximately normal as the sample size increases. In other words, I go out and take a sample and I get a mean of that sample. I go out and take a sample and I get a mean, an average of that sample. As I take more samples, the distribution of those sample means is approximately normal. And if it's approximately normal, then we can use basic laws of probability and statistics to estimate what the population looks like. But how many is larger? Well, I don't know. And the sample size is small, the distribution of that sample mean follows a t distribution, which is kind of wider and flatter. And a z distribution is a pure normal distribution, is actually more peaked. And the t distribution accounts for how many samples you take, and actually you move between 1 to 15. That t distribution, which is really fat and wide, starts to shrink up and look more like a z distribution. You take about 15 to 20, it starts to look more like the z or normal distribution. By the time you hit 30 samples, the t and the z look really, really close. By the time you hit 50 samples, they're pretty much identical. So people say, well, how many do you need to take? Well, between 30 and 50. That's, if you want to start using, basic laws of probability, that's like the bare minimum. But then that doesn't give you a lot of confidence. It just allows you to be more confident in what your estimates are. We'll talk about more of that in just a second. The law of large numbers is also that as you take more samples, you start to get a better view of what the world looks like, which means you're going to get more outliers. because they're going to show up more naturally in your sample. But you're also going to get way more samples that are close to the middle. So as you increase the number of samples you take, just because you're getting more and more and more numbers, that distribution is going to shape like something we can predict. So I'm going to talk really quickly about the t distribution. It's a probability distribution. How likely is something to occur? It looks like a flat or normal distribution. This is what I just said, between n and 30 and 50, that looks more or less identical. So let me switch over really quickly and give you, okay, so here's a sampling distribution from the online stat book, and the PowerPoint has this in it. Let's imagine that the parent distribution looks something like this. In other words, like pretty uniform. When I when I go and take a sample, let's say I take 5 samples, the sample data aren't showing up here, but the mean of those samples is right here in blue, and the standard deviation of those samples is down here. Okay, so I take another 5 samples from this data, which is not normally distributed, it's just a uniform distribution. Take more samples, I take 5 more samples, I take 5 more samples, watch the blue and watch the red. So the blue is the distribution of the mean of the samples. Take more, take more, take more. Red is the standard deviation. The standard deviation is how much variation is there away from the mean on average. So I'm taking 5 more samples. So I think I'm like, okay, 65 reps. Okay, I'm going to keep going, keep going, keep going, keep going, keep going. Now I'm at 160 samples, 170 samples, 180 samples. If I take 10,000 samples, my distribution looks pretty normal, the distribution of the means. And interestingly, the standard deviation also looks pretty normal. So what I'm going to do is I'm going to clear this again. Most data aren't distributed like this that are flat. Most data have some sort of, you know, weirdo peakedness or something like this. So if we do that, let's do, we go here, I grab a sample of 5. This is the animation. It's just going to keep grabbing. It's going to grab 5 more. It's going to show you where they end up. It's going to drop a mean. Okay, so I'm going to do 5 more. 5, 5, 5, 5, 5, 5. Here's 37. 40, 47, 52, 50. Watch, we'll do 10,000. It just pops in. And this is more or less normally distributed. And the standard deviation is more or less normally distributed. So the point of this is that even if you have like a really weird parent distribution, the distribution of the sample mean ends up being approximately normal as you take more samples. Like I hit 10,000 samples, and I've got like this bimodal distribution that looks super funky. I could do that again and take 5 samples. I take 10,000, and you get more or less a normal distribution. So I think it's important to note that no matter what the underlying data look like, the central limit theorem is actually very, very powerful in showing us, like, if the distribution of the sample mean is approximately normal. What that means then is that we can make inferences about a bigger population based on samples that we take. Not the samples themselves necessarily, but the mean of the samples is normally distributed. The average of the samples is normally distributed as we get more and more samples, which means on average, we're getting a good sense of what the population looks like as we take more and more and more samples. Okay, so this is always the question, how many samples should we take? Well, N, how many samples? It's dependent on the confidence limit plus your standard error of your sample squared times the probability distribution. And we always set this to 0.5 and 0.5, so this always ends up being the same. Law of large number says take a lot. Well, it depends on how confident you want to be. So if you want to be super, super confident, you'd change this number here in the confidence limit, and you would, 99% confident, 99% of the time, you'd end up having to take like maybe 6,000 samples, depending on what your underlying distribution looks like. That's the standard error. But let me just like give you an example. I'm cheap. I have 4 kids, a wife, 2 big dogs, 11 chickens, and a mortgage and all that stuff. So when I go to buy pizza, sometimes I look at the special and I try to figure out whether or not an extra large for $9 is cheaper per square unit of pizza than the 2 medium special for $7 each. And so I'll call them and I'll be like, okay, so how big is the diameter of your medium pizza? How big is the diameter of your large pizza? How thick is the crust? And I'll like, measure, because my kids, they're not going to eat the crust unless they dip it in ranch or whatever, right? So then if I'm going to have to figure that out, and to area, I got to figure out the radius is pi r squared, right? So pi times the radius squared. But I've got a decision to make, like how confident do I need to be about the cost of that pizza? Can I like extrapolate pi out to 27 digits? Like, do I need that? Or will like 3.14159 be enough? Or is like 3.14 enough? Well, like how confident, it doesn't make any sense at that point because I'm talking about like pennies, right? If I go out to 50 decimal places, I'm going to get more or less the same answer if I go out to like 2 or 3 decimal places. So in sampling, you have to think about this idea like, well, if I want a general sense, I'm going to have to take a lot fewer samples. But if I want to be super duper precise, it's going to like drive up the number of samples I got to take. So hopefully whenever you think about like how confident you want to be, like 80% confident, 90% confident, like 95% confident, that's seriously confident. I don't need to be that confident about my pizza. I don't, I can round pi at like 2 digits. So you have to just think about how confident you want to be. Okay, so the other thing is we have to assume no systemic bias. That's to say, if our sampling procedures are biased, it does not matter how many samples we take, they will never give us a representative sample. So you can take 75 million samples. If you have systematic bias, it's not going to be reflective of the population. So minimize systematic bias. Okay. So confidence level is the accuracy of the sample statistics. That's to say how confident we are the sample reflects the population. We draw that number from the t-table. The margin of error is the sampling error. That's the amount of error we're willing to tolerate in estimating the population. It's usually plus or minus a certain percentage. When I was doing mining consulting, it had to be 10%. Within 10% of a certain population percentage for density coverage. When we're doing polling for like voting, it's within 3 or 4%. So that margin of error matters depending on what you're working on. Confidence level is about like how likely or how willing are you to be wrong about your prediction. Margin of error is the willingness to tolerate how close you can be to that absolute value of the population, but sometimes you're going to be wrong. So like that's confidence level. Let's say you do this 100 times. If you're 95% confident, then means that 5 times out of 100, you're going to be wrong. And that your prediction, even within plus or minus 10%, that's going to be outside of our prediction. So you have to balance confidence level and the margin of error, the sampling error. So here's 2 examples. If we want to be 95% confident we're within 5% of the true mean, this number 95% comes from the t-table. It's 1.96. 0.5 is how close you want to be to the true mean. This p times 1 minus p based on probability distribution. It doesn't really matter. You can figure that out if you want. I need to take 385 samples. Whoops, I got to go back. If I want to be 99% confident, 99% confident means I'm only wrong 1 time out of 100. Within that same percentage close to the mean, I have to almost double my sample to 664. So the level of confidence matters, and also how close we are. And we can, look that around at the different variations, but most of the time, so this is the confidence limit. It comes from the z-table. Figure out how close you want to be, that's sampling error, and how wrong you're willing to tolerate. And you put those 2 together, and then you put them into that formula, and there it goes. Now, when we were doing field work on vegetation, we just had a running Excel sheet that calculated this stuff for us. We'd take 5 samples, we'd go back and calculate. We'd go take another 5 samples, go back and calculate. But those 5 samples would take us almost an hour to do. So we had to just run that constant calculation. Another way to do this, it does the same more or less math. T, once again, that's confidence limit. The standard deviation, this is S from your sample of all the samples you've taken, and E is a tolerable error. That's the same as the SE before. So different way to do the sample size calculator, but ultimately what most of the time happens is that if you're looking at like really, really big projects, you end up trying to take two pretty standard sample sizes. It's either about 660 or about 1,000. So why are those two? Well, 95% confidence level is 90, you're going to be right 95% of the time. And you can get within 4% of the true mean using 600 samples, or 3% of the true mean with 1,000 samples. If you want to be 99% confident, that number 600 shows up at 5%, sorry, within 5% of the true population mean, and within 4% of the true population mean at 1,000. So those are the two sort of most common sample sizes. Now, if you're dividing it up into like two different groups, like you want to look at males and females, then you have to have 1,000 in each group to adequately estimate with those levels of confidence. So that's why you see things like in political polling, you have 3,000 as the standard number because they want to look at Republicans and Democrats and not affiliated. So that's 3,000 within, more or less three, and they'll be 95% confident. So those are the most commonly used sample sizes. I'm happy to talk more about that in just a minute. Okay, how do we generate samples? The first one is going to introduce bias, and that's going to be totally fine using non-probability methods. These are non-random samples. They're very, very difficult to make inferences about population because of bias and error. Now, some of these ways that we sample are very, very standard, like convenience samples. We go out to a mall or shopping center, we go walk through a neighborhood and see who's out. Convenience samples could be like classes or exit polling. We just start talking to people who are willing to talk to us. Or we start going out and looking at easily accessible vegetated areas, places that are close to certain, freeways. There's a parking lot nearby. It made it easy for us, so we went out and did it. Okay, you can see what the problem is. That won't represent the overall picture of a national park if you show up in Yosemite at the parking lot and you walk 100 yards away and you're in a field. Like, that doesn't give you anything that's going to be reasonably representative of the rest of the park, because those park areas are, where you can park, park. They're not very representative. So convenience samples can be really problematic. A purposive sample is where somebody who's doing the selection of the sample makes a judgment call about what to include or who to include in groups. So focus groups, you'd see this all the time with environmental groups and industry and regulators. You get a group of people who can talk to each other. You put them into a room and you throw out some idea and see how they work it out. That would be like a focus group. But like, let's imagine that I'm an expert on, erosion, and I go out to a certain area and I have to make a judgment call about which area to survey for erosion. Well, it relies on my personal expertise about knowing what areas are going to be most representative, but maybe my expertise is biased, or maybe I'm going to intentionally look for areas that are of one type or another. So purposive sampling introduces bias based on the sampler, and that can be a problem. One of the other ways that we use non-probability methods to do sampling, which is very, very common, it's called snowball sampling. And it's often called like a refer a friend. And we might need to do it for things like gang membership or membership in like Earth Liberation Front or something like that, where you happen to know somebody and you gain their trust. And then you say, hey, I want to know more about this. Who do you know that you could let me talk to about this thing that you're dealing with? And then you start referring a friend and you get more data points, but they're all based on people who know each other or, some sort of connection, which means you might be missing a whole group that either didn't get referred to you, who might not trust you, or maybe isn't known to this other bigger part of the group. So you get data and you get the sample, but it does have some real significant problems. Okay. Valid reasons to use non-probability samples: hard to identify groups, gangs, illegal immigrants, terrorists, whatever it is. Specific groups, you want to just target a certain type of teenager. You want to ask a certain group of people who've been through a project, like a process. If you want to go to specific type of area and you don't care about inferences to bigger, populations, that's okay too. If you want to pre-test something, get information gathering pre-survey, you want to ask some informed people in the environmental realm or whatever about, your process or your method, totally fine. But problems with non-probability samples, Bueller, bias, guys. What does bias do to inference? It makes it impossible, or makes it really, really hard. So whenever you have a biased process, you cannot make good, reasonable inferences to the population. So what we do is often use probability samples. These are sometimes called random sampling, but basically they're all based on the laws of probability. The basic laws of probability involve like every object in the population has a known probability of appearing in the sample, and that every object has the same probability of being sampled. Probability samples allow you to make inferences that you can say, because we know everybody was as equally likely to be sampled, then I know as I grab that sample, it will probably, on average, over the long term, be representative of the population, because I'm not doing anything that's going to bias a certain group or portion or area of that sample. So there's some questions we need to deal with, like how do we generate a sample like that? And what do we do with the sample? It's called replacement. So the basic law of probability is given that all possible outcomes of a given event are equally likely, the probability of any specified outcome is equal to the ratio of the number of ways the outcome will be achieved, the total number of ways that all possible outcomes will be achieved. Who cares, right? Well, just give you an idea, you probably understand that if you break it down slowly. So the blue part is no bias towards a specific outcome. In other words, all outcomes are equally likely. The green part is the ratio. We add that little divided by sign. The red part is the outcome that you want. That goes on the top. And the purple part is all possible outcomes. So in other words, if we're just tossing a coin that's unbiased, we want to see how probable is it that you get a heads? Well, that could happen one way, and there are two possible outcomes. You could get heads or tails. You can get heads one way, so the probability of a heads is 50%. Same thing would go with an unbiased die. If you wanted to get a 4, and there's 6 possible outcomes on a 6-sided die, then your probability of rolling a 4 on any given singular toss is 0.167. Okay, what about a multiple of 3? Well, how can you get a multiple of 3? That could be a 3 or a 6, and there's 6 sides on a die, so you could get that 2 ways, which is 0.333. So, I mean, this is pretty basic stuff. You don't really need to know like these kind of calculations, but you need to think about how likely is it I'm going to sample something if I want to use probability sampling. And there's this question about replacement. Let's deal with that replacement question now, because we're going to talk about simple random sampling, systemic sampling, stratified sampling in just a second. Sampling with replacement is you take a sample and you look at it, you gather the data, and then you put it back in its environment. It's non-destructive sampling. So in other words, I go out and question a whole bunch of students. I let them all go. And then I go out and grab some more students. Those students that I just sampled previously, because I put them back in the population, I have an equal opportunity of grabbing one of those other people as I would any other person. So I could end up surveying a person twice, because if I put them back in the population, nothing changes in the denominator. In other words, in this probability of all outcomes, if I take a sample out from there, it changes the number of people in the denominator. But if I put them back, it doesn't change the people in the denominator. So that's why we do sampling with replacement, is to make sure that all the probabilities stay the same. But you can't do that. So sometimes if you go and you're like sampling the taste of cookies, you can't just put that cookie back in a box. Like, you destroy that sample when you eat it. And because I love cookies, I am the king of using destructive samples, eating cookies. Like, I'll just taste test all of them until they're all gone. So if you're measuring a plant, or you're taking a cell sample, or if you're, going to an undisturbed area, now you're going to disturb it, that whole area now becomes destroyed. It's not It's not untouched anymore. So how do we deal with that? Well, one way is if there's a large population, if there's a large potential sample, removing one of those from, let's say I'm pulling one student, I'm pulling one student out of 40,000 on CSUF campus. Now it's one, instead of 1 over 40,000, it's 1 over 39,999. That probability is more or less the same, and I can be okay with that. But if I'm doing destructive sampling out of like 6 cookies and I destroy one, my first draw was 1 over 6. And then my second draw, when I go get another cookie, it's 1 over 5. And I start changing again, then it's 1 over 4. Like doing destructive sampling on really small samples messes up the problem. It becomes impossible to do probability sampling. But if we're doing sampling, destructive sampling or sampling without replacement on a large population, it's probably going to be okay over time. Okay, so simple random sampling is what most people do. You generate a sample frame, identify all the potential candidates, assign them some random number, use the random number table to identify which cases to include, and you pull them out. So it'd be like Johnny gets assigned to 23. Like you put them in Excel, you generate some random number for them, you sort them based on that random number that was generated, and then you look through this table of random numbers to try and figure out who comes first and who gets drawn. I'm going to show you, oops, sorry. There's a link in that PowerPoint and it goes to statistics how to, and it talks about simple random samples, like why we sample, how we generate it. And it goes through a little bit of that basic, that basic work. So you can look at that if you'd want after the PowerPoint. Okay. Simple random samples are okay. And they work. We generate them all the time. Another way to do a random sample called systematic sampling is we make a list of all the potential candidates for some sample. If every item in that sampling frame is known, and then we divide the number in the population by the size of the sample we want. So we randomize the list of potential candidates, and then we count down from the top every however manyth candidate. So if we got 35,000 CSUF students, and we've got 700 that we want to sample, we generate the list of all the students. Then we somehow randomize it. It cannot be by alphabet. It can't be by birth date. It can't be by class status or credit units, because then what we've done is introduced some systemic bias in our sample. It has to be absolutely randomized. Then we count down. Every 50th person gets to show up in the sample. That's 35,000 divided by 700. So start at a random point, pull every 50th person, those become part of our sample. That's systematic sampling. Okay. When we do simple random and systematic sampling, these are relatively unbiased samples, limited technical difficulty. Simple random samples and systematic sampling end up not giving us a very good idea about who could be in your population that are very small groups. So for example, you might not get subunits of the population that are relatively small proportion of that population. My very first concert that I ever went to was by the Dead Milkmen. So this like punk group in the late 80s, early 90s. And they, so I don't mean to be offensive, but they talked about the left-handed lesbian Eskimo midget albino student union at their university. And I thought that was pretty funny. But let's imagine that you're looking at, how well distributed those are, that group of people are in a campus. A simple random sample or systematic sampling is never really going to pull those 5 people out of a group of 35,000 individuals to show up in a random sample. If you're just looking on average and you're not looking at subgroups, you're probably going to be okay. But this is also going to be a real problem if you're trying to do a simple random sample for like endangered species. By definition, they're very, very hard to find. They're not going to show up in a random sample. So if you're looking at big, broad averages, simple random sample and systematic sampling do really, really well. If you're looking for hard to find groups, you're not going to find those groups. So another way to do sampling that is based on the laws of probability is called multi-stage stratified sampling, or multi-stage or stratified sampling. It's more technically complex, but we do it all the time now. And what you need to do is sort of look at the population and identify some subgroups, subunits of the population. These could be like different types of individuals by race, ethnicity, class, status, whatever that is. Or it could be like a specific vegetative area, and you have some wetlands, and you have some highlands, you have some, some other sort of riparian areas, and you have some desert landscape. If you know what those different areas are, and you can identify what they look like in the total population, what you can do then is go and take a random sample from each of the strata. And then you can take that that simple random sample from the strata, and based on how much of that area that each of those strata occupy in that whole population, or what percentage of the population is a certain group, then we can weight that sample information to give you a general idea what that population looks like. So I'm going to just show you really quickly. I did some work on a coal mine in Burnham, New Mexico, and I've got a bunch of these in other places. But we'll just look at this one to give you an example. So we had to do a reclamation bond proposal for this little square area. Let's see if we can zoom in for you a little bit. This is in Burnham, New Mexico. This square area right here are the boundaries of the mine that was disturbed. But the mine itself, if you follow this fence line up, you can kind of follow where my cursor is, and around the whole area of the mine that they had bonded was up through here. And before they started disturbing the central area, they did a survey to see how much of this area was this type of vegetative zone, and how much was this sort of saline sodic soil, and how much was this other type of soil. So what we did was we had to go out and say, well, this portion of the disturbed should look like this portion up here. And this portion of the disturbed area should look like this portion over here. And this portion of the disturbed area should look like this portion right here, if we've gone back and put the vegetation back and created the soil environment, and so that we can get these kind of plants to grow. So what we had to do is we had to sample this whole area using these different strata. And then we'd sample this area, and we sampled this area down here. And we got those 3 different estimates of what the vegetative cover were and the species diversity. And then we went out to the natural environment outside of the disturbed area, and we figured out what the average vegetative cover and diversity was. We went out to this other one that matched up to this other disturbed area and figured out what the vegetative cover was, diversity. Did the same thing over here. And for each of these separate areas on these disturbed areas, we had to make sure that they were in compliance with those separate areas. But we also had a vegetative standard for the big square that had to be a composite of all of these together. So we had to do these different strata and sample there, but then we had to do a composite to make sure that that whole area was covered properly. So just to show you that, like, it's very, very easy to do if you're using a map, if you're using that sort of thing. But if you're looking at a population, you have to rely on like a census to figure out, how many people of a certain race, ethnicity, gender, socioeconomic status are in a certain group of population. And then as you're going out to do like let's say we're doing like a social survey, you have to hire a survey firm that can make sure that you get a certain number of each of these individuals, or at least a random sample of individuals who meet each of these criteria, so that you can re-weight your survey data so it'll be representative of the population. Not really that hard, it's just a little bit technically complex. And this will, because it's based on the laws of probability, give us a population estimate, or sorry, a set of statistics that will be really representative of a population estimate. So how do we know if a sample is representative of the population? Well, you can go through all those steps that I just talked about. If we're using primary data, that means we went and gathered it, looked at the sampling frame. Is the way that we constructed the sampling frame representative of the population we want to build, like we want to infer to? Are we bounding it based on time? Are we bounding it based on a certain area? Are we missing some sort of the population that we want to catch that's not in your sampling frame? So defining your sample frame is really, really crucial. And then are we using some sort of instrument either to generate that sample or in some measurement tool that's biased? Because if the measure's not valid, if our instruments are
off, is our collection process not reliable, not repeatable, then no matter what kind of numbers we get, it's not going to be representative of the population, because there's some error that's introduced either through, some systemic bias, or, a variety of other ways. So that's if we're doing it ourselves. If we're gathering data from secondary data, can we trust it? Is it from a reputable source? Is it transparent? Have they talked about their methods? Did they clearly write out, like in their technical appendix, where they got the data, how they generated their sample, what was their process? And I promise you, if they're not transparent about that, then it's probably not reliable data. So that's important. And then also, is the data that we get out of these secondary sources, is it really tell us what we want to know, or is there something wrong in their measurement? Or, you got to just be critical consumers of that information that you're exposed to. Okay. So there are a variety of ways to obtain a sample. Some have more bias than others. And if we talked about measurement before, you'll see that even measurement has bias in it. Every sampling procedure has a potential to introduce more bias. So what we need to do is find a way that we can either reduce bias and error, like a probability sample, so that we can efficiently make some inferences about a population, or we can use a non-probability method where we throw, inferences to the population out the window, but we rely very heavily on expertise from an individual sampler or from some other process that we think will yield a very, very good representative sample, but we have to just assume that responsibility for that bias. We can either take on that responsibility for the bias using a non-probability method, or we can give that bias to basic laws of probability and let that work out, using math and the law of large numbers and stuff. So sometimes it's justified to rely on non-probability samples, like endangered species surveys and stuff. But almost all the work done by scientists, social scientists, relies on some sort of random samples. So that's more or less what I've got. If you're doing like social survey work, this is a note that you should be aware of. Sampling is really, really crucial in survey work. You need to know, are you contacting or getting people into the sample, the people that you're targeting? And one way to look at that is response rates. The response rate is the number of completed surveys divided by the number of invitations you made to participate in the survey. So when I ran the Survey Research Center at University of Kansas, we would invite 100 people into our pool, our sampling frame, 100 numbers. Then we were calling on the phone all the time. And we would call those numbers like 10 times at different times of the day, using different callers, all sorts of different days of the week. And we would do that because as soon as a person is in that denominator, as soon as you invite them in, the only way to increase your response rate is to get them to complete a survey. So you wanted to get the fewest number of invitations possible and the most number of completed surveys. And back then in the early 2000s, 60% is what you're looking for response rates. Now, if we introduced 1,000 individuals into the number of invitations, and we started calling them, calling, and we got 300 completed surveys, because that's where we were going to stop when we got a 30% response rate. That doesn't mean that if we would have worked, that's not a good thing, because maybe if we would have worked harder, we could have bumped that number up to 600 or a 60% response rate. But because we hit our number already, we're going to stop. Well, as the response rate goes down, in other words, as it comes closer to like 10, 15, 20%, the sample starts to look like a convenience sample. And it's not very representative because you just happen to get the right people at the right time when you called. That's why you don't add 1,000 people to the invitation list right at the beginning. You slowly add the number of invitations to try and get them to actually participate in the survey, because the quality of your data is going to get better. Now, some people will be like, well, I launched a survey on Instagram. I launched a survey on Facebook. I launched a survey on LinkedIn. Okay, that's totally fine, but you can't judge the quality of your sample data because you can't track the number of invitations you've sent. So you can't calculate a response rate. So even if you get 600 people, it doesn't, on my Facebook feed, let's say I've got 300 friends, maybe you got like 1,000 friends because you're cooler than I am. But like, if I get 300 people who see my post, I'm pretty sure that 300 people don't see my post. the number of people who see my posts is based on the Facebook algorithm, and not everybody's seeing it. Like I might only get 50 people out of that 300. So like you have to be cautious about how we do these things. Like you might send an email to somebody and track them down to see if they've completed their survey. But if you've done that, then it's no longer an anonymous survey. Maybe it's a confidential survey. So you have like sort of these combinations of potential problems with sampling, confidentiality, measurement, response rates, geographic area that you're covered, all these sort of like get thrown together. But I needed you to think about social science surveys, talking to individuals, and why response rates were super important. If we were in person, I would have you do a sampling exercise. I've got 3 bags of marbles, and you dig your hand in and you figure out how many of a certain color are in your hand, and then you put them back in the bag. Now, I don't think I'll ever be able to do this again because of COVID and dirty germs, and you can't sanitize all the marbles and all that stuff. But what happens is, I think I have the marbles data on your website. What you see is in the first 10 samples, the first 10 marbles, you get an average, and it's pretty close, probably within, 20% of what the true distribution of that color of marbles is in the bag. But the more time you take samples, you get closer and closer and closer to the true mean all the time. And your level of confidence goes through the roof. So maybe some other time we can do that, or we can do some applet, but I just want to tell you that that's actually true. The more samples you take, the closer you are to the true mean. And I wish that we could do this some other way, but as far as I can tell, I don't think we can. So I'm going to turn this off really quickly.